Last thing I want to talk to you guys about is gravimetric analysis. Gravimetric analysis is a way for us to determine the composition of a sample based on a reaction. So we're going to take a mixture of something, we're going to dissolve it in water, and then we're going to add a different compound to it that's going to cause something to precipitate out. Once it precipitates out, whatever precipitates out is a specific compound. We're going to analyze that, and we can then back calculate to figure out how much we had of something originally in the sample. For this example, we have a mixture that contains sodium chloride and aluminum sulfate. A 1.4 gram sample of this mixture is dissolved in water. Okay, so basically what I've got is I've got a beaker. And that's a really bad drawn beaker, I apologize. And to this, I'm going to add some sodium chloride. And some aluminum sulfate. I'm going to add both of these in here. Now, we haven't explicitly talked about solubility rules yet, but we will get there. But the way this is written, saying dissolved in water, tells me that everything in here is soluble. What's it going to look like in solution then is, so here's my water. I'm going to have sodium ions floating around and chloride ions floating around. And I'm going to have aluminum ions floating around and sulfate ions floating around. So they're all just floating around minding their own business, okay? I'm then going to add excess sodium hydroxide to this. Excess meaning it's not going to limit how much precipitation can be produced. I'm going to add sodium hydroxide, and when sodium hydroxide goes in, it creates more sodiums, but it also creates hydroxides. So the sodiums are the exact same, but the hydroxide is important. The precipitate formed tells me here that it's solid aluminum hydroxide. So I don't have to know my solubility rules yet. The question's going to tell me it's aluminum hydroxide. What happens in solution is this aluminum hydroxide, they find each other. And of course, I need, 3 hydroxides for every aluminum. But they're going to find each other, and it's going to crash out as AlOH3. Or let me put the parentheses in the right spot. AlOH3. So every aluminum is going to grab 3 hydroxides for itself, and it's going to crash out as a solid. So in solution, let me redraw all this. Hopefully you paused that video or you rewind, because I didn't think to warn you guys before I erased all that. So you've got this beaker. And now in solution, you've got sodium ions still floating around. Got chloride ions still floating around. And you've got sulfate ions still floating around. But on the bottom of the beaker, you've got solid aluminum hydroxide. That aluminum hydroxide is filtered out, dried, and massed. The mass of the aluminum hydroxide we find to be a value of 0.107 grams. What I want to know is what is the mass percentage of aluminum sulfate in the original sample. So again, pause if you need to draw this out. First thing I need to do to figure this out is I need to figure out what reaction I have going on here. I need to figure out how many things are reacting in this system. So I know I've got sodium chloride, which is actually just acting as a spectator. But I'm going to include it in here anyway, just for right now. I've got Al2SO4 aluminum sulfate being reacted in here. And I'm going to add an AOH. All of these are aqueous or soluble in water. I'm going to produce aluminum hydroxide, which I know is going to be solid form, S for solid, because it says a precipitate of solid aluminum hydroxide. I've got sodium chloride, which again, they're just acting as spectator ions. And I'm going to also form Na2SO4 aqueous. I don't care much about that. It's not what's important in this question. You're going to figure out why when we do chapter 5, how I know that. But it's called a double displacement reaction. Basically, the aluminum takes the hydroxide, so the sulfate is going to combine with the sodium. In truth, they're all floating around independently in solution, but it's called a double displacement, and it's driven by the formation of this solid product here. Now that I have a reaction, though, I need to balance it. So the sodium chloride on each side is already balanced. I can actually ignore it because it is a spectator ion. But I'm going to put it in here right now just so that we can see it was in the mixture. I've got 2 aluminums here and only 1 aluminum on the other side. I need to put a 2 in front of here so that I have 2 aluminums on each side. We do cover balancing equations in the very next chapter, so you're going to need a lot more practice with it, but we do need to know how to do it for these, okay? And by the time you get assessed on these, you're going to know how to balance equations. So you guys got to get comfortable with it. We've got 2 aluminum, 2 aluminum. I've got 3 sulfates here. I need to put a 3 in front of here, so I have 3 sulfates over here as well. Now, I've got 1 sodium here, but now I've got 6 sodiums over here, because again, I'm ignoring the sodium from the sodium chloride. I'm going to put a 6 in front of here to balance out my sodiums. Now I've got 6 hydroxides here, and I see I've also got 6 hydroxides here. So my equation is actually balanced now, which is what we needed. Because what I really care about here is the relationship between the aluminum sulfate and the aluminum hydroxide. That's what I'm going to need in the next step. So I'm going to do a stoichiometric conversion here. I want to know the number of grams of aluminum sulfate that I have that could produce this much aluminum hydroxide. I know that that aluminum sulfate is going to limit how much aluminum hydroxide can be made. So if I can figure out if I know how much aluminum hydroxide I made, I can use that to determine how much aluminum sulfate must have been present to produce that much aluminum hydroxide. And I'm going to do this through stoichiometry, which is done through a balanced equation. I write down what I want to know first, and then I write down what I'm given. I'm told that I isolated 0.107 grams of aluminum hydroxide. Now I need to figure out how to get back to grams of aluminum sulfate because I want the mass percent. So I need the grams of aluminum sulfate in the original sample. I know I can only compare between moles, so I know if I have 1 mole of aluminum hydroxide, that is consists of 78 grams of aluminum hydroxide. So exactly 78 grams of aluminum hydroxide equals 1 mole. I also know, based on my balanced equation above, that 1 mole of aluminum sulfate reacts with 2 moles of aluminum hydroxide. So I'm going to say times 1 mole of aluminum sulfate to every 2 moles of aluminum hydroxide. Now, if you want to stop and check right here, it's a good place to check. This cancels out my grams of aluminum hydroxide. This cancels out my moles of aluminum hydroxide. I now have moles of aluminum sulfate. Since I have moles of aluminum sulfate, I know I can quickly convert to grams of aluminum sulfate. There's 342.17 grams of aluminum sulfate in every 1 mole of aluminum sulfate. Forgot to write the little tubes there. It is Al2SO43. And if you check here, this cancels out the moles of aluminum sulfate, and now I have grams of aluminum sulfate left. Put this in your calculator, and it doesn't matter which way you do this. You can say, 0.107 divided by 78 divided by 2 times 342.17. You can do the multiplication first, then the division. Doesn't matter by orders of operation. Just make sure that you're plugging in the right numbers and multiplying and dividing where appropriate. and you should find that this had 0.235 grams of aluminum sulfate. What does that answer mean? First of all, it's not the answer for the total question yet. We're close. What this means, though, is that if 0.235 grams of aluminum sulfate are required to produce 0.107 grams of aluminum hydroxide. And some students get thrown off by that, like, but the number's less. Yes, but you're producing something else. The sulfate, which is adding up to the difference in mass here, is still residing in solution. So now we are ready for the next step, which is what is the mass percent of aluminum sulfate in the sample? So the percent of aluminum sulfate is going to equal your grams of aluminum sulfate divided by the total grams of the sample times 100%. We know that we had 0.235 grams of aluminum sulfate, and our original sample was 1.45 grams. When you calculate that out, I'm going to run out of space here, we find this is 16.2% aluminum sulfate. So 16.2% of my entire sample was comprised of aluminum sulfate. The other roughly 84% was actually sodium chloride. Let's work one more example for gravimetric analysis. So chloroisodiamine, C14H18Cl6N2, is a drug used in the treatment of hypertension or high blood pressure. A 1.28 gram sample of the medication containing the drug was treated to destroy the organic material and to release all the chlorine as chloride ion. When the filtered solution containing the chloride ion was treated with an excess of silver nitrate, 0.104 grams of silver chloride was recovered. Calculate the mass percent of chloroisodiamine in the medication. I have one too many D's there. Oops, wrong button. I apologize. Spelling is not bad for me, but not always the best. There should be one less D there. In the medication, assuming the drug is the only source of chloride. So I'm told that I got this whole compound. Cool. This whole thing used to treat hypertension. I'm going to take an entire 1.28 gram sample of the medication, but I'm going to treat it to destroy all the organic material. Then that leaves the chlorine as a chloride ion. So I'm going to have chloride ions floating around. The filtered solution containing the chloride ion is then treated with excess silver nitrate. So I filter it, I pull off just this guy, and I add it to silver nitrate. In excess because that we're going to learn about limiting excess reactants in the next chapter, but that means that all of this will react, and we don't have to care about how much of the silver chloride I have present. I then recover 0.104 grams of silver chloride. I want to know the mass percent of the chloroisodiamine in the medication, assuming the drug is the only source of chloride. So I've got Cl minus, chloride ion, is going to react with silver nitrate to produce silver chloride, and then nitrate ion will be left over. This reaction's already balanced. I have one chlorine, one silver, one nitrate, so I don't have to balance anything. What I need to do to figure out the mass percent of the drug, I'm assuming that the drug is the only source of chloride, which means if I can figure out how many grams of chloride are in the sample, then I should be able to figure out the mass percent in the overall medication. So number of grams of chloride. Chloride and chlorine will have the same mass, 0.104 grams of the silver chloride. Convert that to moles. And now that I've got moles of silver chloride, cancels out that, I can go ahead and use the balanced equation to find moles of chloride. I've got moles here. If you want to check, moles of silver chloride is canceled out. I've got moles of chloride ion, and I want to figure out the mass in grams of chloride ion. Now remember, again, electrons weigh very, very little, so 1/2000th of an AMU. So the fact that I've added one electron to make a chloride ion does not change my mass. It's still going to be 35.45 grams of Cl minus for every 1 mole of Cl. This cancels out my moles of chloride and gives me grams of chloride. And when I calculate this out, I find the answer to be 0.0257 grams of chloride ion. I want to know the mass percent of the drug, assuming it's the only source of chloride. I know I'm using a 1.28 gram sample. What I can do here is I can assume that I know that the chloride is the only thing coming from that drug itself. I know that first thing I can do is I can figure out the percent of chlorine in the sample, and then I can figure out the overall mass of the sample from that, and then I can go ahead and figure out the total answer. So I'm going to run out of space again because I problem with writing on one little screen. I'm going to write up here that I know I have 0.0257 grams of chloride ion. Okay, so go ahead and pause the video if you need to write other things down. I know that the entire compound here is C14H18Cl6N2. I'm going to figure out the molar mass of that, and I did not think to write this down. So 1 second while I do that. So I've got 14 carbons, 18 hydrogens, 6 chlorines, and 2 nitrogens. So 14 times 12.01 plus 18 times 1.008 plus 6 times 35.45 plus 2 times 14.01. I get a molar mass here of 427.4. The percent chloride in sample is equal to 6 times 35.45 grams per mole divided by the total mass of the sample, which is 427.4 grams per mole. So even though chloride, we've only got 6 of them in there, it actually constitutes the bulk of the compound. It is 49.77% chloride ion in the sample. So I know that 49.77% of it is due to chloride. I know I have 0.0257 grams of chloride in the sample itself that was analyzed in the sample. The original sample that contains the drug and dissolved all the other material away. So what I can do from there to figure out the mass of the actual compound in the sample that was analyzed. I apologize. I am on vacation at my mother's, and it is really nice outside, and everyone is on their motorcycles today, and we live on a main drag. So the mass of the chloride sample, I know if I have 0.0257 grams of the chloride ion, I'm going to divide this by the percentage of just the chlorine in the sample, because this will give me the overall mass of the total sample, 0.05163 of the total compound. Ah, 164. Sorry, that's what I was checking to make sure I'd written down my numbers correctly. I hit something on my calculator. There we go. So I know that this is my total C14H18Cl6N2 sample of the 1.28 gram sample of medication that contained the drug. It contained 0.05164 grams of the actual drug. So we got, you got the whole medication, right? You got this whole medication with all its binders and everything else that goes into making a medication. Then we've got the drug itself, and then we've got the chloride sample within there. So we figured out the chloride sample. Now we figured out how much of it's actually the drug, and we know the total system is 1.28 grams. I hope that makes sense what I'm saying. If not, come see me in office hours and I will help you understand that a little bit better. But I know that if 49.77% of the sample is due to chloride, I've got a 0.0257 grams of chloride in the sample analyzed. That means the total sample had to originally weigh 0.05164 grams for that drug within the overall sample. Again, pause if you need to write anything down because I do need the space. And now what I want to find is the mass percent of chloroisodiamine in the medication itself. So I know I have 0.05164 grams of C14, H18, Cl6, and 2 in 1.28 gram sample. Times this by 100% to figure out the percentage. And let's go ahead and do that. 0.05164 divided by 1.28, multiply that by 100, and we find the answer to be 4.03%. Note that I have 3 sig figs here, so I'm going to keep 3 sig figs at my final answer. And so the mass percent of chloroisodiamine in the medication, assuming the drug is the only source of chloride, is 4.03%. Again, if you want more practice with this, I highly recommend it. Look at the additional practice problems at the end of the PowerPoint. They start here. The video, they're also in your student notes. The videos are worked out. The video for that is worked out and online already for you. Please go ahead and watch through those. Work the problems on your own first. Use the video if you get stuck. You've also got online homework, and your textbook is an excellent source of more problems. Good luck.